Hey
Salut,
Stefanella, ça va?
salut. Ah, maman. Ah, voilà.
T'es chez toi là?
Oui, oui, oui. Ça va, ça va.
Donc vous êtes confiné?
Oui, mais bon, ici, c'est le chaos, c'est le Brésil. Pourtant, quand tu sors, plus que la moitié n'a pas de masques. Voilà, parfois, c'est seulement 10% qu'il a des masques. C'est le
Ouais,
chaos, c'est le chaos.
ouais. Et
Vraiment,
les hôpitaux sont
les,
saturés?
sont saturés, mais comme tu sais, nous, c'est seulement 25% qui c'est privé. Les
Ouais.
publics, ils sont bien, mais ils sont moins que ça. Et donc, il y a la plupart de la population qui n'y a pas de... Tu
Qu'il
vois,
n'y a pas
moi,
de...
Non,
Ouais.
moi, j'ai une femme de ménage qui vient chaque 6 mois, comme ça, et elle habite près d'ici. Elle et son fils, ils ont le Covid et maintenant, ils ont la tuberculose. Tu
Aïe,
vois.
aïe, 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 aïe.
Oui, oui. Et là, c'est moi qui je lui dit quoi faire avec le Covid. Bon, bien sûr, il n'y avait pas de problèmes de respiration trop graves, mais elle avait des tosses et tout ça. J'ai dit, prends la vitamine D, c'est con zinc, fais les vapeurs. Et ils se sont curés comme ça. Ils se sont
Ouais,
curés comme ça.
d'accord. Aïe,
Donc,
aïe,
moi,
aïe.
chaque fois, je dois croiser les doigts qu'il n'y a personne, qu'il y a comment dire, des problèmes auto-immunes, non, parce que la vitamine D.
Ouais, ouais.
Mais bon, en général, ça marche. Tu vas faire. L'alternative, c'est pas d'avoir des docteurs. Et
Ouais.
là, j'ai trouvé un médecin qui fait de la télémédecine. Mais bien sûr que de temps en temps, il a besoin de quelque chose, de mesurer quelque chose. Et là, il avait besoin de l'oxygénation,
Ouais.
ça qui, alors, elle a dit, va à la clinique de la famille tout près de toi. Et là, parce qu'il avait une autre, la nièce de cette personne, elle était obèse et tout ça, donc elle avait des problèmes de respiration, des fatigues, tout ça. Et quand elle allait à la clinique, tu sais, cet appareil, ils se sont refusés de lui faire la mesure de l'oxygénation. Donc, on ne sait pas si c'est parce qu'ils étaient pleins, elle avait l'air bien, ils avaient peur qu'il peut-être il va s'infecter, ou parce que l'appareil, elle était disparu. Ça, c'est plus
Ouais, ouais,
probable, tu vois.
ouais.
Et donc là, on a pensé, attends, je vais faire entrer Guilherme. Là, on a pensé, voilà, peut-être, ce qu'on peut faire, nous, on peut donner des appareils comme ça au comité association des résidents, mais avec un protocole, parce que ça ne disparaît pas, tu vois.
Ouais, ouais, bien sûr.
Et alors, mais c'est tout comme ça, c'est tout comme ça.
C'est pas bon ça, hein? Ouais,
Non, non.
ouais.
Et attends que j'étais, on va faire. Donc, voilà, là, il y a Guilherme.
Euh,
Guilherme, il a passé 6 mois avec Bedreddin en Seba et en Bordeaux. C'est
d'accord.
maintenant, il commence un master. Hein.
Et ouais, bon dia.
Guilherme, il parle français, il a appris
Ah, il
français.
parle français, très bien.
Mais
Il était chez
six
qui?
mois à Bordeaux. Bordeaux.
Ouais, il était chez qui à
Bedreddin.
Bordeaux?
Bedreddin en Seba. Bedreddin.
D'accord, je vois pas qui c'est.
Bon, c'est le grand chef là, de l'épidémie.
D'accord.
Mais il fait plutôt EDP, transport. Il s'intéresse à des modèles structurés par âge, tu sais, ce type
Ouais, ouais,
d'équation de transport,
d'accord.
un peu à la pertame, mais bon.
D'accord.
Voilà.
Hmm.
Et voilà, il a dit bonjour, Guilherme.
Bonjour Guillaume.
Donc, il a dû apprendre, parce qu'il est arrivé en janvier, il est reparti à la fin de juillet, donc il a dû apprendre français pendant la pandémie, voilà.
Aïe, aïe, aïe. Ouais.
Mais
Ah,
je
c'est une
crois qu'il
époque
a,
bizarre, hein? Je sais pas si...
mais il a envie de retourner en France pour le doctorat.
Ah, d'accord, bah, c'est bien, c'est une bonne
Et
chose.
il préfère les petites villes à Paris.
Ouais,
Il a
il a raison.
préféré,
T'as complètement raison, Guillermo. Ouais,
il a préféré largement Bordeaux à Paris. Il a
ouais,
trouvé que,
ouais.
que Paris, c'est trop chaotique.
Et actuellement, nous, on est en état de siège, comment on appelle ça?
Oui,
Couvre-feu.
oui, oui. Lockdown.
Rouen, Paris, Lyon, Marseille, couvre-feu.
Mhm,
Et tout l'ouest reste libre pour l'instant. Donc Bordeaux reste libre, par exemple.
mhm.
Parce qu'on a des chiffres qui remontent, les chiffres deviennent, commencent à faire peur, en fait,
Ah, oui, oui, oui.
pour la saturation des hôpitaux, si tu veux.
Oui, 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 oui. Mais justement, il faut qu'on parle une autre fois parce que justement, nous, on a vu qu'il y avait différentes phases de saturation des hôpitaux. Ici, par exemple, c'est clair qu'il y a la saturation aussi de personnel. Parce
Ouais,
que ici, il y a une grande, beaucoup plus qu'en Europe, des médecins et des infirmières qui passent ce moment infectés sont morts.
bah oui, non, c'est clair. Ouais.
C'est énorme ici. Et donc, on a eu des hôpitaux avec des lits, mais pas des médecins, parce que
Ouais,
les gens
ouais,
ils ont peur s'il n'y a pas d'équipement, s'il n'y a pas
ouais.
d'équipement, s'il n'y a pas de tests et tout ça. Et
Ouais, c'est
les
très
gens, ils
difficile.
ne vont
Ouais,
pas,
ouais,
ils ne vont
ouais,
pas. Et
ouais.
donc, voilà, donc on est dans cette situation-là. Après, les journaux, ils disent, ah, il y a des... C'est pas vrai, il y a des lits pas occupés, mais il n'y a pas de médecins.
Ouais, ouais.
Ça va peut dire parce qu'il n'y a les lits sont libres, qu'il n'y a pas des gens qui pourraient les occuper, tu vois. Mais bien sûr, tout c'est mal reporté. Et voilà, on a ce type de problème. Tu veux essayer de voir si ça marche là? Je t'ai donné
Allez, faisons. Let me see.
Et alors là, donc il va voir Corrado, c'est notre étudiant d'initiation scientifique. Et Gabriella aussi. On est en famille ici.
C'est ce que je vois. Est-ce que vous voyez mon slide?
Yes, on le
OK,
voit.
excellent.
Bon, c'est mieux parler en anglais parce que les autres, ils ne parlent
Ouais,
pas.
on va attendre un peu.
Et donc, je laisse entrer. Yeah, so we speak English. So here we have some students from, not only from UFRJ, from other part of Brazil also.
OK.
It's been interesting.
OK. Where are you from, Conrado?
Corrado?
Hi, good morning.
Good morning.
Can you hear me?
Yeah, I can hear you.
Yes.
Well, I'm from UFRJ,
OK, where is
Rio de
that?
Janeiro.
He's our university.
OK, OK.
No, he's one of ours, but he wants to know where are you from originally?
Oh,
No?
I was born in Nice, near the Italian border. So I'm Italian. I was Italian like Stefanella at some point in my life.
Caputo. And Corrado, where were you born, Corrado? Carioca or not Carioca?
No, actually, I'm from a city in the interior of the state.
Okay.
Guilherme as well. Guilherme as well is
Okay.
from.
Interesting.
So let's wait. People are a little bit late.
Okay.
My computer this morning was a little bit funny. So I have to, one second, I have to send an email to the people to send the link.
Okay.
To the, so give me 5 minutes there.
Sure.
My computer is not very collaborative this morning. So, but the university are still open.
The university is still, yes, the university is still open. I'm teaching some classes remote when there's a lot of students, and the rest I'm in presence. So yeah, I actually don't mind the remote teaching, you know.
Well, yes, but it's different. I mean, like you cannot have many students. In my point of view, you cannot have more than 30, and that's okay. And then students ask. But if you have a lot of students like fall off, they don't ask, and then
yeah, that's true.
And this is a big controversial, at least here, because there are people that think is because it's remote, they can 300 is the same.
Yeah.
For me, it's not the same, but of course, everyone is entitled to have, you know, their opinion. I mean, and maybe there are different methodology. I mean, if you give class to a lot of people, then you have to have a very good TAs that they work on small groups. So anyway, you need many people.
You need the TA, yeah, for sure.
Yeah, you need very good TA because our TA, they're not trained, so it's not their fault. So what they do is that to help the student sometimes to solve the problem, but the student making the work, they provide the list of exercise with correction. So the student just look at the correction.
Right.
So, but you know, of course, they were not trained, you know, so how to encourage a student to work and so on. So, you know, they should be trained. So, but anyway.
You're right.
So, 1 second. By the way, we need some statistic people. So after we talk, I need your statistic people urgently. We have lots of data.
Okay. Yes.
Okay, 1 second. Okay, so I think we are all set. Some people are entering. Okay, so Samuel, I think I will start recording, and then I would like you to just give a short for the student to know about the, how your academic formation, where you study, and postdoc, so the students see even the interdisciplinary character, how it came to how you got to work on and learning the tools Okay, so I just let me start the recording. Okay, so we are very pleased actually to have Jean-Guy, that is a colleague, but I would say he's also a friend, and we always look for a new problem to work on, and hopefully we will manage soon to tackle some epidemic problem. And he's coming to us from France, from Rouen, that is very charming city. Normandy is a beautiful region of France. People know heard a lot about Paris, but we were talking about the quality of life in some of the other part of France. And in my point of view, Rouen is a very nice, charming town. And the university is, whenever I visit, I had a great impression, very kind of family kind of life. And this kind of environment is very precious to work on. So please, Jean-Guy, you are very welcome. So please tell us.
Thank you, Stefanella. So thank you also for the invitation. It's a pleasure to be virtually in Rio. I've been there already, so I know the place. I think it's a beautiful area. So let me, as you requested, let me say a bit about how I got to do what I'm doing. I did my PhD 30 years ago. That's a long time. I was in Grenoble at that time. I was an engineering student, and this was the mid-'80s. We were examining data from the point of view of dynamical systems. So think of some data coming from some experiment. In those days, the experiments that were very in fashion were Rayleigh-Bénard, where you heat fluid from below and you have convection rolls established and so on. So this would produce data, and so I did my PhD was on how to validate these methods that were put forth. These methods were called, Takens was involved in the development of these methods. You build a pseudo phase space, then you do statistics on your data, and you essentially understand what is the dimension of the manifold on which the data lives. So that was my so I've always had one foot in physics, another one in mathematics. And so then I went to Arizona as a postdoc, and I learned soliton theory from Newell, Alan Newell. And that was a good school. I learned a lot from those guys. It was an amazing time in those days because there were a lot of good people in Arizona, and it was a very interesting time. I go back to Rouen. I got a position there. Have to thank the French system, because in the French system, you get a position very early. If you're lucky, you get the position, and you can develop what you need to, what you want to develop. So that was a good, it was a very good time. I worked with a good collaborator from Heraclio, Nikos Flitsanis, with whom we did a lot of work on St. Gordon. And from then on, I continued. I worked on different applications of nonlinear waves, some dynamical systems. So that's the story, more or less. And recently, with Arnaud Knipel, you see Arnaud Knipel is right here. He is my colleague from the department where I'm at. He's a specialist of graph theory and networks. And with him, we started doing some network stuff. I bring the dynamic side, and he brings the operations research side, the optimization side. And we developed this model of that I'll present today. And we applied it. It turned out we could apply it to the current epidemic. So that was a bit of a surprise to me when I started off. So let me tell you about the people involved in the work. There's my Mexican colleague, Cruz Pacheco, Gustavo, his student, Fernando Bustamante, my student, Fatima Muatamid, and another student, Yunyi, with whom I worked this summer. Okay. We were funded for part of this work by the French Research Agency and by the region of Normandy. Okay. So what is the work about? Can you all see the slide, or should I make it bigger? It's fine. Okay. So what I want to show you guys is how good a simple model like the SIR, the really basic SIR model, can be, and how much you can get out of it, coupling it with the data. So I'll first derive the analysis of the SIR, and I'll show you the data in conjunction with this analysis. And then I'll go on with the model, specifically the model that we studied, which is the SIR plus the graph. Okay. Using this model, we could suggest some isolation strategies. We could predict the arrival time of the epidemic to Mexico, and also analyze what's happening now. In France right now, we're having a second wave. So things are getting complicated, probably not as complicated as in Brazil, but things are getting complicated. So anyway, let me show you the SIR. So you probably everybody in the audience knows it. This is the SIR. So was introduced in 1920 by Kermack and McKendrick. These researchers, they were English researchers, they were interested in modeling the influenza. The Spanish influenza killed something like 5 million or 20 million people in the 20s. It was a very deadly disease. And so they introduced this model. It's just a 3-compartment model. You have the susceptibles, S, you're infected, and you're recovered. By recovered, of course, could be the dead as well. Okay, it's just what happens after you get infected. The coupling is your standard law of mass action coupling. That's the coupling you find in the Lotka-Volterra, for example, when you study ecosystems. And so immediately what you see from this model is you add the equations and you get S plus I plus R equal constant. So that's one property. I plot here the evolution, the time evolution, a typical time evolution of S and I. Okay, I didn't plot R. So what happens is you have your susceptibles initially equal to 1. Your infected grow because of this feeding mechanism, alpha Si, and then they saturate at some point when there's not enough S, and then it goes back down. So the dynamics of I is this green curve here. Start from 0, you go back to 0. The dynamics of S, you start from 1 and you go to some value which is small or which can be not so small. So we'll come back to this. Typical important parameter is this alpha over beta. You see here, if you factor I, you get alpha S minus beta times I. So I will grow if at time 0, alpha S minus beta is greater than 0. Okay, and since S equal 1 initially, this is just this ratio R0, which has to be bigger than 1. Okay, so what I'm going to try and convince you about is that this model is a good model to describe what's happening. Okay, you don't need to go into more details at this level. First of all, because you have few parameters and you want to match them with the data. So the fewer parameters, the better. That's one thing. Second, you want to analyze this model. I'm a theoretical guy. I like to understand what's going on. If the model is too complicated, then there's nothing that can be understood. It's too difficult to do any analysis. So the first simple things that can be done are to understand what's happening here at this peak. What is the value of S star? What is the value of I star? And what is the time at which the peak will arrive, T star? Okay, so I'll sketch the derivation. It's very simple. You can it's easy to do. I just check. Well, first of all, let me give you the values. This is S star, 1 over 0. I star is more complicated. It's this, and this T star is given by this integral here. Okay. So let me show you how you get this. It's an integral on S, so it's implicit. Let me show you first how you get S star and I star. So you start with these ODEs. Okay. As I said, N is a constant. The total number of susceptibles infected and recovered is constant. The epidemic occurs if alpha S minus beta is positive. And immediately you see that ds equal dt equals 0 means that, I'm sorry, it's not ds over dt equal 0, it's di over dt equals 0, this value here. This value here is immediately given to you by writing that this right-hand side is equal to 0, okay? From this, you get S star equal beta over alpha, 1 over R0, okay? So that's the first value. Then if you want to get I star, how do you do it? You take this equation, the I dt, this one, the S dt, you divide the second by the first, and you get an equation as a function of the IDS. So the IDS equal -1 plus beta over alpha S, which you can integrate, gives you this, I equal I0, etc. And at the maximum, I star, you write that S is equal to S star. And this is your I star. So you see, very easy to get S star and I star. The time T star is more complicated. So let me go through the derivation. You can invert this equation, ds dt, and write dt by ds equal -1 over alpha si. And then you substitute your I of s in here, and you get an equation that only depends on s. And you can separate, okay? You write everything that's t on one side, everything that's s on the other side, and you integrate, and you get your T star, okay? You're going to tell me what's so interesting about the T star. Well, the interest is that you can predict the peak. If you know what's happening at the beginning, if you have an idea, you can predict at what time it's going to peak. And this is very important for people who do who manage the epidemic, who decide on the number of hospital beds and so on. They need to know when it's going to peak and more or less how much it's going to peak. So with this we predicted that it peaked in France on around April 20 or something like that. Okay. So anyway, that just to tell you how important these numbers are. So what do people do? Typical public policy decision is you don't want to be saturating your hospitals, okay? So you want to reduce the intensity of I. So what people do is they reduce the coefficient gamma. Okay, actually this guy should be alpha, but they reduce this term alpha Si. So you see, I'm sorry, it's this guy. We go on the left here, beta 0.25. You see how far how up it goes. Beta equal 0.15. You've reduced it strongly. Okay. The price to pay is if you look at the S infinity, the value down here, that for the susceptibles, you get 0.1 here, you get 0.4 here. So I'll come back to that. And that's a problem. Okay, that's a problem. So anyway, let's see the data. And this is the data for Germany in pink. The data is coming from Worldometer and John Hopkins. And in green, you see the fit. And you see that we can catch the maximum pretty good with this very simple model. There is a trick, though. The trick is that you need to have a coefficient that will tell you for a number that you have in your database how many people are really infected. Okay, so there's a multiplicator here that enables you to adjust this thing. Typically, the multiplicator we found is about 50 to 100, closer to 100. Okay, so for one case reported, 100 people were sick, about. Okay, this is what where we were able to match the data. So this is Italy, for example. You see March 1st, April 1st. And you see again, we can capture pretty much the value. The values of alpha are here, alpha 0.32, beta 0.18. Beta is the time for it's the incubation period typically. So about 5 days here. Here we had to change the incubation period to adjust it anyway. So this was expected. We also had unexpected behaviors. Okay, of course, you do a simple model, things are not going to work as nicely as you expect. For example, this is Spain. You see, it looks like there's a first maximum coming here, then there's another maximum, goes down. It's a bit chaotic. Iran's even worse. You have what looks like a second wave coming in. Already on May 1st, you have the beginning of a second wave in Iran. So we didn't understand this. This was, I mean, this doesn't fit with the SIR. So you have to add ingredients to the SIR to make it work, or to make it describe these different situations. So let me show you the world situation. This is up to June. So things start in Hubei. Okay, this is Hubei in pink. Then Italy. Okay, there was a large community of Chinese people around Milano, and this is where a big cluster started in Italy. The epidemic in Italy was concentrated in those northern regions. It didn't hit as bad in the south. Anyway, so this is Italy, France in black, and you notice that it stabilizes. There's not a well-defined peak. This was a bit surprising, but the number of active cases is difficult to estimate exactly. This is Iran I was telling you about. You see, so another peak starts, another wave starts on May 1st. Okay, first wave, not so big, and then starts again. The USA is in yellow here, and it starts, and I'll come back to that. It's here, it's still increasing. So the data, both in Iran and Spain, told us that we had to look more finely we had to coarse grain things. And there's a website in France called Veille Coronavirus. You can look it up. And this is the data from April 5th. The people in and out from the hospital. So it's a snapshot of the number of people in the hospital due to the disease. So you see, there was a huge cluster in the Paris region, large historical cluster on the east. Okay. This is Lyon and Grenoble. And you see the west, I live here, actually on the river here. And in Normandy, it was not so bad. We didn't get it so bad. All the west pretty much was, didn't get it so bad. You look at the numbers, 700, 400, compared to 2,000 or even 3,000 here. So there was a definite propagation ingredient in the problem. Okay. So if you look at the data on the same graph, this is what's happening.
Can I ask, what about the main train? If you go back to that map, Isn't a train line, the fast train line that goes through from Paris to the east through that region?
Yes, yes, there was.
Okay.
But historically, what happened is that in end of February, there was a huge cluster that started in the region of Mulhouse. Mulhouse is around here, and a lot of people got infected. There was an evangelical reunion, and people got infected, and they infected. This spread out to Strasbourg and also to Paris, because some of these people that were attending this meeting were in Paris, were living in Paris. So they got infected, they brought it back to Paris. They got infected, they brought it to Lyon or Grenoble, you see?
But it could also be the train from Paris to Marseille, because also this is another,
course.
you know,
Yes.
two at the crossing of two paths.
Exactly. You have, as Stefanella says, there's a fast communication, fast train line from this blob here down here, and also to this one. So there's clearly some disfavors, and also to the north. Okay, so that definitely you can relate it to that. Yeah. So anyway, so we said, let's look at the data more carefully, and we suggested this model here. So I'll tell you the model, and this is the model. So let me explain to you the details. We developed this with my Mexican colleagues, and one of the first things that one can think about are road networks. Okay, so here are the six main cities of Mexico. You have Mexico City here, Pachuca, Querétaro, Guadalajara, Zacatecas, and Puebla to the south. So these form a graph. Okay, this is the graph. And using this graph, what did we do? We said, okay, let's assume that on each node of your graph, you have susceptibles, Sj, infected, Ij, and each node has a capacity, Nj. Okay. The point is that Mexico City is 30 million people. Puebla is like 3 or 4. So the ingredient, the coefficient here that compensates is this Nj. Nj is equal to 30 million for Mexico and to 4 for Puebla. Okay. So this is your SI. And how do you couple the SI? Well, we said we couple it to the neighbors. Okay. And here I'm summing over the Ks that are neighbors of J. So for example, 1 is coupled to 2, is coupled to 5, is coupled to 3. Okay. 5 is coupled to 1, is coupled to 4, is coupled to 6, and so on. Okay. So this model was introduced by Brookman and Helbling in the context of influenza in 2013. The thing is that Brookman and Helbling, they assumed a non-symmetric coupling, which means that the flow from 1 to 3, for example, was not necessarily the flow from 3 to 1. Okay. If you do that, you lose a lot of the nice mathematical features of the model that I'll tell you about. Okay. So we decided to go the simple route, assume symmetric couplings. and assume the same epsilon, okay? Because now you can also play the game where you put weights on your network and have some different weights. So for now, all the weights are the same. We just assume some diffusion epsilon. Okay, so I'm coming to it. So the model is well posed and positive. I won't go into that. I'll refer you to our paper for that. That's not that interesting about the model. What is interesting is that you can write it using the graph Laplacian. So let me show you. This is the equation. So I have my graph here. And I write this in matrix form, where delta is this matrix that I'll write below. S is the vector of with S1, S2, Sn, I the same. The Si is the Hadamard product of the two vectors, okay? And delta is this graph Laplacian matrix. So let me tell you how you build the graph Laplacian matrix. The node 1, you see, is, so the graph Laplacian, its diagonal is the degree of the graph, the number of links of each node. And then you have your adjacency for the non-diagonal terms. For example, 1 has degree 3, so you put -3 here. 1 is connected to 2, to 3, and to 5, so you have a 1 here in 2, 1 for 3, and 1 for 5. Okay, so it's a 6 by 6 matrix. You can write the same for 2 and so on. And you get this matrix. When you look at this matrix, you should be very happy. Okay, and why does it make us very happy? Makes us very happy because it is symmetric, you see, and it's also positive. So that means that I have the slide. I should have put the slide for this, but you know the properties of eigenvalues and eigenvectors. So eigenvalues are the matrix is actually negative. Eigenvalues are negative, and the eigenvectors, you can choose them to be orthogonal. Okay, so you can do some analysis that is very nice, because you're going back to something that looks like Fourier. You're doing a spectral approach on these problems. Your operator delta, it's a self-adjoint operator, it's symmetric. So you have all the nice properties that you have with these orthogonal eigenvectors and real eigenvalues. Okay, so this is the model. Okay, and let's first let me go first through the analysis or the numerical analysis of what happens. Okay, so first we started so there's a historical aspect to this. We look at the influence of the diffusion epsilon. Okay, the first situation is when you have a large diffusion. Okay, large diffusion is the left panel here. I'm representing I, and I start the infection at the node 6. So node 6 is here in black, and you see how it propagates. It propagates fast. It propagates first to node 5. This is this curve here. And then from 5, it reaches 1 and 4. 1 and 4, very close. And then from 1 and 4 reaches 3 and 2. Okay, so large diffusion, everything's happening at the same time, pretty much. Okay. Now, the other side, the other limit is small diffusion. So it takes time to go from 6 to 5 and 4. So you started at 6, you have your peak here. This is essentially an SI peak. Okay, the peak that I was showing in my second slide. Then things come down in 6, and then you excite 5. 5 goes through the peak, then 1 and 4 together, you see, and then the rest 3 and 2, and there's a slight shift. First reaches 3 and then 2.
I'm sorry, Julian, what's the difference, the situation between the two? What was the...
The difference is epsilon equal 0.1
yes,
on the left, and 10 to the minus 7 on the right. Okay, and it's an interesting situation. When we first started playing with the model, we were looking at this limit here. And the limit for the epidemic, the limit for, it's more this one, at least at the beginning. And this is one of the things that we learned with my Mexican colleagues. The epsilon has to be small. It starts first in China, then it moves over to Iran, then to Italy, then to France. You see? It's not happening all together. So anyway, that's some lesson. I'll come back to that. So from this, another thing that can be done is to look at the epidemic criterion. So epidemic criterion, we're generalizing what Kermack and McKendrick did, which was to say, okay, let me go back to it so I can show you. You go back to your standard SI model, and you see you factor I here, and you get epidemic if alpha s minus beta is positive, the IDT positive. Okay, so you can play the same game with this vector or graph model, and I'll show you. Here we're looking at a matrix M, which is your epsilon delta minus beta identity plus the diagonal alpha s. So let me show you again. You see that this, you can, it's a linear, assuming s is constant, you can you can factor I, and you get this matrix here. So you get an epidemic if one of the eigenvalues sigma I of M is positive. Okay, that's this means the IDT will grow. And let's examine the eigenvalues of M. And this is one of the things you can do with this analysis. As I was saying, delta is symmetric, it's non-positive. So the eigenvalues, they're all on the left-hand side of the imaginary axis, and they're real. You're on the real axis. The largest one is 0. Okay, we're assuming a connected graph. Okay, if you had several disconnected components, you'd have several 0 eigenvalues. Okay, we can choose the eigenvectors to be orthogonal. Okay, and an important eigenvector is this, the one corresponding to the 0 eigenvalue, the one corresponding to this guy here, and it's the flat vector, the Goldstone mode. So things, if you're assuming that your S and your alpha are homogeneous, so you have the same alpha, same S everywhere, then what you're doing is you're just shifting your eigenvalues from 0 to something positive, which is alpha S minus beta. And it grows from there. And it grows, how does it grow? It grows together, all together. Okay. So that's one of the lessons from this. Another thing that can be done is you can look at what happens. So this is what I was telling you. You see, M is diagonal, it's real. So there's two limits. If epsilon is small, then pretty much there's no coupling. You see, each node develops independently. Okay. The situation is not so interesting because you want to see what happens at the level of the network. So you want epsilon to be significant so that it will interact with these terms. So as I was saying, if S is homogeneous, the largest sigma 1 that dominates is the one corresponding to the goldstone. It's the flat state. Okay. If S is inhomogeneous, then it's a different story. You can have other things happening. It's more complicated. So let me go back to the outline and tell you where I'm at. So we've covered the basic analysis of the SIR. I've looked at the data. I've introduced the model and this isolation, and the properties of the model. And we come to the isolation strategy. Okay. Again, the nice thing about such a simple model, it's linear, and you can say some properties about it. Okay. So in particular, you can decide what you're gonna do about your graph. I should make a picture here because it would be better. Let me try and add a share and add the so can you see the blackboard? Okay, so let me draw this this 6 graph. So I have one here connected to 5, connected to 6, 4 is here, 3 here. There's a connection here, connected here, and 2 is here. So what is the strategy of isolation or vaccination is you have the epidemic starting, and at some node here, for example, you want to vaccinate. So you want to prevent the epidemic to grow here. So what do? You do alpha equals 0, for example, here. So the epidemic will not grow. Okay. And so what did we do? We looked at the eigenvalues of the matrix if we isolate these different nodes on the 6 graph. Okay, so let me go back to the slide and show you. So I look at my graph and I vaccinate, let's say, node 6. Node 6 has degree 1, you see? So I expect that the degree will change the way the matrix will behave. Okay. Anyway, this is what these are the results here. You see that for degree 6, my eigenvalue remains positive. It's still unstable.
We don't see the result. We just see the whiteboard.
Okay, so let me kill the whiteboard, and let me go back to the okay. So degree 1, I'm sorry, for node 6, you don't change your eigenvalue that much. Okay, node 2, you reduce it. Okay, it's 10 to the minus 2 here, 10 to the minus 3. If you vaccinate node 4, node 4 has degree 2, you are able to bring down even more the eigenvalue. Nodes 1, 3, and 5, you're getting it even further down. Okay, so what's the message here is that without vaccination, I'm sorry, the message is that it's most effective to vaccinate the high degree nodes. Okay, it's somehow you could expect it, but it's nice to find it from this model. Okay, something I should have said, the largest eigenvalue of M is 2.5 10 to the minus 2. So you see, vaccinating even a degree 1 node brings it down a bit. Okay, so that's one of the results. Okay, have a caveat to say about this is that to observe this, you need to have your Laplacian acting. Okay, so there's a window of values of parameters where you will see this effect. If if epsilon is smaller than 1, the nonlinear part takes over. I mean, the S part takes over, and you don't see anything anymore. If you're above 1, then you have then you're killing the epidemic. So you have some sort of a window where you can observe this. So we can play this game with another with vaccinating now 2 nodes. This is what's done here. So you take nodes that can be neighbors or that can be not neighbors. And what you find again that it's most effective to vaccinate high degrees, and it's most effective to vaccinate not neighboring nodes. Okay, so for example here, high degrees, degree di is equal to 2 and 3. It's better to vaccinate these 2 guys than to vaccinate the same or to vaccinate 2 and 3 here, but that are neighbors. You see, 4 and 5 are neighbors. You get minus 9 10 to the minus 3, and between 2 and 5, nodes 2 and 5, the eigenvalue is much smaller. Okay. So this is the situation. You can make sense of this using the Courant veil inequalities on the symmetric matrix of the Laplacian. We have a little time for this. I can show you this in our paper. I had not planned to show it, but since there's a little time, I can show it. So I'll stop the share and
also, Jean, if 5 minutes break in the middle is good also.
Okay.
Whenever you think is a good moment. People
Okay,
got a coffee.
You're right. I'll just flash this and then we take a break.
Great.
So can you see the PDF? So the analysis is actually tricky. It's not it's not so trivial to get the fact that isolating high degree nodes is the best way to bring down the eigenvalue. Okay, so what we did was look at the Rayleigh quotient, this quantity here, which is the maximum eigenvalue of M, and this quantity here, we found inequalities on it. And if you write di, the degree of node I, you can get this result, so that sigma 1 is greater or equal to minus the minimum of the degrees plus beta s minus gamma. We assume that these guys are homogeneous, S homogeneous and beta homogeneous. Okay, so if you're isolating a degree that a node that has not smallest degree, you don't change the estimate, and this is one of the results that you can get out of this analysis. And conversely, if there's a unique node of minimal degree and you isolate it, then you change the bound. You see, so these are the kind of things that we did, and this needs more work actually. This part. So we're pushing it right now, trying to understand it better. Okay. So anyway, let's take a 5-minute break, and we'll resume.
Great.
Okay.
It will be great to see how this works with the neighborhood in Rio, for example. It will be very nice to see how, we have train systems, we have, especially with the train. Well, the problem here that we have a lot of buses and people move chaotically. So, but, imagine to take only the metro and the train, just, I mean, of course, there are the buses that are the main thing, but, these are more out of control. So more some general diffusion by buses. Maybe one can repeat. I have another question. You say that you said that when you were showing this peak, you said that the epsilon, small epsilon, was more likely to represent the reality because we see first happen to China, then period later see. But we can think about the critical mass. Okay, I explain what I mean. I mean that there are a lot of asymptomatic. So before it gets, the tip of the iceberg get visible, you need a lot of serious sick people. For example, even here, apparently we have suspected cases at the beginning of January, but then it became like officially in March. So it's because, and then we have Carnival. Imagine, imagine the staring, you know, Carnival was everyone mixing and then goes back home, you know. Actually, I was in Spain and sharing an apartment with other people, and one guy from England spent Carnival in Rio, and he got tested positive the next week, you know. We just overlapped 1 week because, you know, he took over what I was leaving my room. But anyway, so you have this event. So people realize this was already there with a great delay. And this, I think, is because of great asymptomatic, you know, the large number of symptomatic kind of make it hidden for a time, you know. So this could, you know, this is about the visible, you know, these peaks.
Right. Yes.
Are the visible, and then who knows if we take in account the symptomatic, you know, how really how the shape would be different, you know, it would be more spread.
Yeah, you're right. But for in this model, the asymptomatic are included in the second box. You see, they're the infected.
Yeah. Yes.
SI model. And,
yes, but
and it's true that
we observe the data are the one that, at least here, I mean, they're the one that are really sick, and then they enter the system, because most of the people that are sick don't even go to the doctor, at least here, and so they are not visible.
Right.
You see, they're invisible.
Yeah.
And so this kind of, even when I was in Spain, I was living in Spain. At the beginning, they were saying everyone go to the hospital, and in Barcelona they had the reference hospital, the clinic, and they tried to organize. You know, say, okay, that is the hospital, so all the infected go there. But then it went out of control, and so they were saying, stay home. And before they were saying, okay, you stay home, and they would send you the test home, and then there were no more tests, and so, you know, this it went out of this control. So this I mean, anyway, so this critical mass, this is what I mean about critical mass, that the visibility.
Yeah, you're completely right. I talk with doctors in France, and they were our doctor friend. She was telling us that she was already seeing cases in December.
Yeah, actually, we had a colleague that she came, I don't know if it was the end of November, beginning of December, and she got all the symptoms. She even lost the smell or the taste thing. So she had all, and it was the beginning of December, something like that. Yes. Right. So, but then, you know, it was sparse case, and maybe she stayed in their hotel, and she didn't go so much around, you know, like, you know, you had the things that they don't spread, you know, like, so, and then boom, you know, this is what, I mean, I think here, of course, was Carnival, because, you know, it became visible right after Carnival.
So Carnival was
at the end of February,
and it was not postponed, it was not canceled.
No.
Oh my God.
Yeah. In fact, I've seen this bulletin where there are these cases after the Carnival. You know, you find things after.
Course. Sure.
Because of course, you know, we you know, we have lost we have blew the things, but no, we didn't know after there were suspected cases since before. So it was the next Carnival is canceled. But, you know, people are already thinking to come to Rio for New Year's Eve. and of course it's the same. You know, you have 2 million people in the I think, I'm not sure that this is confirmed because Carnival is canceled. I hope that they cancel as well this big, huge celebration of fireworks on the Copacabana beach. But there are people, they're asking for a place to stay and they're planning to come. And actually, this was the thing. If you compare Rio with other towns in Brazil, even with this mess of the hospital and so on, because we had somehow reasonably locked down, it was lower. Okay. And it was recovering, but then suddenly they opened the beach, you know, and then and then people from outside came, and then boom, you know, like so you know, you have to have a coordinated policy all around the country, because you know, if you preserve reasonably one region and then the other do whatever, and they're free to come, and then everyone mixed suddenly, you know, so. But it's hard. It's hard because people to stay home, you know, like they're used to be outdoor. Here they're very sociable. They're used to go out to eat, to go to drink. Yeah, it's a very interacting population, and of course it's hard, you know, even with that. But anyway, so it's a population is used to be outdoor, you know, and to see friends and to see family. And in fact, you can pin down even when there was Easter was another peak, you know, like you can pin down some of
the events. It's interesting.
The events, you can pin down like in Italy was the same. Like for example, in Italy, they closed the school the 4th of March. And then people in the north of Italy, they thought it was a good idea then to take vacation to do skiing altogether. So people from Milan to Veneto, they went skiing in Alto Adige. And so you see that suddenly in Trento and Bolzano, boom. You see, I have the curve actually, I want to show you, because it's really like the Soliton, you're Soliton, boom. And then like a week later, I mean, not even a week later, a week later, the 8th of March, they closed the ski slopes. But the things was done, you know, that weekend, everyone was there.
Damage is done, of course.
So, and then they did the same in Italy, like when they were isolating Lombardia. And then at the beginning, and the number were going down, and then suddenly it's okay, you know, let's reopen the train. And this is the train that goes from the north of Italy to the center and to south. And so people that they have family in the south and the center, and they were losing their job or whatever, they didn't want to stay there, or you know, they didn't have any more the need. You can actually you know, if they didn't even have more the job and the money, you know. So anyway, they flee. They all took the train and they went to the Danube, and this is where you see the boom. You see, so. Or you have another event in a little town in my region. It's 90,000 people. Pesaro. You see, it's 90,000 people, and so you say, what the heck? And what you have that you had the final of the basketball championship. Wow. And all the team from the north of Italy, they went down there, and then suddenly they all saturate the entire town. You don't see there in the town, you see that in the regional data, because the hospital system is regional. So if they don't go there, they go to another hospital in Ancona, because they distribute in the same region. So you see that the number of people in Ancona were increasing, but it's not Ancona, it's from Pesaro. You know, and you know this because you have to know someone within the hospital to tell you this, where they come from. And at a certain point, they start to get infected people from Ancona, but then they didn't have any more beds there because they had the people from this small town. They had this championship, you know. Usually, they don't have problems. So that's very small hospital because it's a town that doesn't have huge problem. But then, so you have all these things. You have to pin down events in order to understand some of these peaks. Usually.
Do you have in Italy there's good access to data? The data is good?
I have the data if you want.
Okay, interesting. Okay.
And
I've been coming from Ministerio di Salute?
Yeah. So Ministero of Salute.
And you have the data region by region?
Average by region, yes.
Okay.
And sometimes there is also town, but the one of the town, they are not as complete as the region.
Right.
You have the town data, but the one of the region, they come from the people in the hospital, from, you know, they have people in quarantine, they're more complete.
Okay.
They're people, but you have also some town to town. But as I say, town to town, it will not tell you the other thing. You have to know the history, because you will see Ancona increasing, but it's not Ancona, it's the other town. So it really, you have to know how the hospital system work in order to interpret. Like it doesn't make sense in Italy to speak about Italy. It makes sense to speak about region. This is the scale. This is the scale. This is the scale in Italy that it really makes sense.
I think everywhere. Huh?
Yeah,
in France,
I'm saying about Italy because it's the way, it's the system that I know it works. You know, like for example, here it's very I don't know, because here you don't have the public system very strong, so you have the private system has somehow more occupancy, so it's hard to know, you know, how it works. So
it's hard to get numbers for Brazil or for the Rio de Janeiro area.
We have some number. It's a little bit hard that we, for example, you know this, you have noticed some people are in some hospital, but then you don't know, maybe the hospital is in Rio, but maybe some of these people that come from another city again.
Okay. Yeah.
So you have to kind of match different database,
right,
for doing this. So for example, now we have a group of people researching, even one of my students, they're analyzing the RNA COVID data in the lab to see the different kind of evolution in different regions. But then you don't know exactly if the patient in that hospital, you know, is exactly from Rio or is from some other town. You have to cross a lot of database to make sense.
To understand that. That's
to understand.
Okay.
So it's a little bit more complicated. I feel the Italian data are easy to read.
Right.
They are more organized. But I would be happy to talk to you, because I think
we can talk a little bit.
We can cross more.
Yeah.
Or, you know, another time. Yeah.
No, my talk I have about 10 more slides to go, and after that we can have a discussion, huh?
Okay, so let's have 5 minutes, okay?
Yeah. Okay.
Yes. For a coffee.
Right. O café da manhã.
coffee. Cafezinho, cafezinho. So, yes, so we can go ahead.
Okay. So we were, let me share the screen again. So this was the situation. I was describing the eigenvalues of M, and I went through this isolation strategy of killing the alphas on one of these nodes, and showing that the largest degree nodes are the ones that you should vaccinate to bring down the eigenvalue. Okay. So let me tell you the other another part of the study, which was how we applied this to the start of the epidemic in Mexico. And we said, okay, we predicted it to be around March 20. So what we did was consider a complete graph. This is the complete graph. You have here Hubei, Beijing, Shanghai, Japan, Western Europe, Eastern USA, and Western USA, and here Mexico. Okay. By this, I want to emphasize that the connection between the connection of the world between the connection of the world with Mexico is less than, for example, the connection of the Eastern United States with the Western United States. There's, in a way, you could say that the weights of the graph are large here and weak here. Okay, so if you do the dynamics on this system here, you start the epidemic here, 1. It reaches everybody else, 2 to 7. 7 is here. It reaches 2 to 7 all together. You see, this is 2 to 7. And then it has to cross over and reach 8. Mexico is 8. Okay. So in other words, the epidemic has to travel from Hubei to the rest of China and then over to Europe and the United States before reaching Mexico. Okay, this was our understanding, and the same probably happens for Brazil, apart from the carnival episode that we were talking about. But on a regular basis, people travel less frequently to South America than for example, from Europe than to the rest of Europe or to the US or whatever. Okay. When you isolate Hubei, this is what happened in this was in January 20. They cut off Hubei and they only connected Hubei with the rest of China. So you have a connection Hubei, Beijing. Beijing is still connected to these other regions, but the connection between Hubei and there's only one link between Hubei and Beijing. If you do the dynamics here, what do you see? You see that it starts first here, Hubei, goes over to Beijing, 2. From Beijing, it spreads simultaneously to the complete graph. So this is 4 to 7. And then reaches 8, reaches 3 and 8. So 3, I forgot why there's a different dynamics here between 4 and 3 and 8. But anyway, the point is that you shifted a bit, okay, because of the time it has taken to cross over from 1 to 2. Here, there's no, once it's in 2, it's in 7. Okay, here once it's in 2, it has to cross over to 7, and so on. Okay, so using this very simple model, we estimated the diffusion coefficient. Okay, remember in our model, let me go back to the model. There's 3 parameters. You have your alpha, you have your diffusion epsilon, and you have your beta. Alpha and beta are given by the doctors. This you know more or less. Beta is the doctors. Alpha is the rate at which the epidemic develops in each node. So you know these numbers. The epsilon you don't know. Okay, and so what we did was estimate this, and from this number that we got, we were able to predict the arrival. We estimated this number to be 10 to the minus 6. So small diffusion, actually. That's the point. So to continue with the work, another
I'm
thing.
sorry. How was before? This is this epsilon 10 to the minus 6 is after being isolated. How was before, the value before?
It was probably around the same value. It was probably around the same value. It takes some time to cross over from one node to another. You see?
But the geometry of the graph is not reflected in the epsilon.
No, not really. No, we talk the same.
It's just reflected in the infection, infection parameter. It enters in the infection.
Right.
Okay.
What's happening here is the topology. You see the time it takes to go from one to the neighbor.
Yes, I understand.
Is due to this
the spreading.
Right.
The traveling wave. It travels
exactly
through different paths. Let's say.
Exactly.
It takes longer path to get there because it's less connected.
Because you've cut off all the other links.
Yeah. The topologically, as you say, is different. Okay.
Exactly. So this is a. So we got the doctors very the doctors in Mexico. We got them very interested, and we provided advice to the Ministry of Health of Mexico with this kind of very simple, very basic ideas. You know, told them to check the borders, to check the cruise vessels that would arrive in Cancun or in Acapulco. You know, this kind of measures, and make sure that this link somehow was controlled, so that you would not have many infected people coming here. If you could reduce the weight here, you would be able to delay the epidemic. You see. So that was what we did. So historically, I was visiting Mexico at the time. I was in Mexico until March 8th, working with my friends on this on the problem, and I was sending emails to colleagues in France, telling them to worry about the situation. because the situation was, it didn't look so bad in France early March. It deteriorated very quickly. So another thing that can be done with the model is to look at confinement, and confinement, deconfinement, and also the second wave. Okay, so how do you play with confinement? Well, you can play two ways. One is to reduce the alphas, the coupling at each node. Okay. The other one is to reduce the diffusion, what we were talking about earlier. Okay, so let's go through these situations. And this is this last section of the talk. So let's look at what happens when you increase alpha. Okay, so this is two situations. I just have one node here, okay, and A is the situation where I do nothing. B is the situation where I'm changing something. Okay, so what do I change in B? In B at t equal 30, I change abruptly alpha from 0.33 to 0.5. Okay, and you can see the following. Okay, here if I change the alpha before the peak, I have a huge burst here of infected. These are the infected. Okay, so it's really not good to be deconfining before you hit the peak. If you deconfine after you hit the peak, like here on the right, then it's not so bad. You see, B is very close to A. Okay, compared the two situations, clearly here you have an overshoot. Here, nothing much happens. Okay, so this was the picture that we had, let's say in June, or we didn't completely realize the situation. The situation actually is more complicated because you have to consider prevalence. Let me tell you what is prevalence. We go back to SIR, and let me go back to SIR. SIR, you have the three quantities. You have S, you have I, and you have your recovered. Your recovered actually measure how much of the population has gone through the system. How many people have actually gone through and gotten the disease. Okay, so it's very important to get this number once the epidemic has passed, once the wave has passed. Okay, so let me go back and show you this. Once the disease has passed, you can say that the number of people who actually got the disease is the value of R at infinity. The value of R at infinity, you can compute it, and I'll show you how to compute it. You have to, there's an intermediate step, which is to solve for this S infinity, and you plug it back in, and you get R at infinity. Let me show you how you do this. First, you have your conservation law, and at infinity, the wave has passed. So I is equal to 0. Okay, I'm assuming I'm not changing any of the parameters here. I'm just looking at what's happening. So you have S plus I plus R equal S infinity plus R infinity. Okay. At t equals 0, you have S plus I plus R equal S0, because I is equal to 0 and R is equal to 0. So you just got S0 here. You use these two equations and you get this. R infinity is 1 minus S infinity. So now let's find S infinity. You remember that we had an equation I as a function of S. It's written here. Okay, so this equation relates I to S. From this, you can obtain what happens at infinity. And at infinity, you have this, I0, and you get this guy. If you assume I0 to be 0, S0 to be 1, which is the case for the COVID-19, then you get S infinity, which is this nonlinear relation that has to, S infinity solves this guy. Okay, so from this, you get S infinity. From S infinity, you get R infinity, which is the value, the prevalence, let's say. So let's see with the data. Okay, and the problem with mitigation, remember mitigation, we reduce by confinement the value of alpha from, let's say, 0.25 to 0.15. The price you pay is that the S infinity here is 0.1. So a lot of the S's have been consumed. On the other hand, here it's 0.4. Okay, so not many S's have been consumed. You get a prevalence here of 0.9. 90% of people have been infected here on the left, whereas only 60% of people have been infected on the right. Okay, so in fact, you can get a second wave. Okay, so let me show you what happens here. What I did here is I have my first wave here. R0 is 1.2. I'm above 1, so I have the epidemic. It's very flat. And then all of at this level here, I increase brutally R0. Okay, and what's happening here is that you still have some S's that are available to have another peak. And this is one of the mechanisms to get the second wave. You release or you increase contacts very quickly, and then you get the second wave this way. So that's one mechanism. Okay, and this is probably what's happening here in France at this moment, where we're having a second wave due to this. Okay.
Summertime. In Italy, everyone went to the beach, they meet at the beach.
Exactly. So people go and have weddings and
exactly.
parties and so on, and you get this second peak. Okay, so that's one thing. That's one strategy to play with the system. Another strategy is to play with diffusion. And let me show you what happened. And this was something we were very scared about in May when they deconfined France. Early May, they allowed travel from Paris to Normandy, to our region. So typically Paris, 20 million people, our region, 1 million or 2 million, but not more than that. Very small number compared. 1/20th about. Okay, and I'm going to illustrate what happens on this two-node graph. So we play the same kind of games. The A is things have not changed, and B is when you change something. Okay, so what do I do here with B? I change the diffusion at time 15 on the left before the peak, and at time 22 to the right after the peak. Okay, so I'm allowing travel between Paris and Rouen, my Normandy city where I live. I allow it more. Okay, Before May 10, no travel was possible. After May 10, people could travel. And this is what we saw. Okay, so if you allow the travel before the peak, then you have a huge increase of the peak. This is your left panels, I1 on the top, I2 on the bottom. So you see you have a huge overshoot of I2 because of these imported infected. Okay. On the contrary, if you allow travel after the peak, what's happening here is that the peak in 2 is prolonged. So you see you go this way and you continue going this way. So you have the infection continuing. And nothing much happens to Paris. Paris still goes down. Okay, so it's very interesting to look at what happens on the world level. This was taken last week from the New York Times website. Look at Israel. You have 1 bump, 2 bumps, and then another bump. The Czech Republic is more monotonic. Argentina is monotonic. The Netherlands, you have 1 bump and then another. Belgium, 2 bumps. France, 2 bumps. UK, United States, several bumps. Brazil, apparently things are slowing down. If we believe this.
No, in Brazil we have 2 weeks, at least 2 weeks of delay. So it looks always is slowing down, and then you have to trace back 2 weeks earlier. So okay. You have 2 weeks of notification because of the notification system.
Oh, so you say for administrative reasons
you cannot trust the last 2 weeks. Okay. You cannot trust what it comes here today is of 2 weeks earlier. So right. you have to revisit. You have to relook what happened 2 weeks earlier because it has been updated and was not there 2 weeks ago. So you have to chop off the last 2 weeks. Right. So I don't know in that graph, maybe, so it looks more a plateau usually. It doesn't go down.
Right. Yeah. So anyway, I thought I had put Iran here. Iran is not here, but anyway. So you see there's many situations where you have these oscillations because the policies have been relaxed, because mobility has been allowed. You know, there's very in France, for example, look how low it goes. So we thought that things were quiet after that, and then they relaxed the contacts, they relaxed the mobility, so then boom, it goes back up. So anyway, so that's the story. Let me flash you the conclusion slide. We analyzed this model of an epidemic on the network. This model is basically an SI. Okay, there's nothing more than that. It's a good model because it can be fitted to the data. Okay, it has this importation of infected. It has the minimum number of parameters, so you can understand things. We generalized the epidemic criterion, found that it was best to isolate high-degree nodes. Okay. From the point of view of the model, maybe the mobility should be improved, because diffusion, it's nice for the mathematics because you can do things, but maybe it should somehow be improved, but still remain tractable. So we don't really know how to do this. With this model, you can do recommendations. You can tell people what they should, I mean, the politicians, what they should be doing, confining early, masks. They should avoid super spreading events. They should avoid carnival. They should avoid all these events, football games. There's many examples of
basketball games as well.
Basketball, whatever.
Volleyballs.
Yeah. And you should deconfine slowly, and be careful with the deconfine. And the last thing is that modeling this thing is difficult. It's very humbling. We cannot do much. We are relying heavily on data, and if the data is not good, then we have trouble.
And also there is one thing is that once I was listening to a talk about Ecuador, and there were, Ecuador also small, but there are people from all over the world that go to Ecuador. Mm-hmm. And I was really impressed because they say in Ecuador, they had 4 different COVID circulating. They had one from US, one from China, 2 from Europe. Wow. They were comparing the strands. Apparently the US and China were closer in genomically with respect to whatever it means, because also whatever it means, but anyway, with respect to Europeans ones. And so even here in Brazil, imagine if in Ecuador, they were able to find 4, imagine in Brazil with all the mixing, even the evolution, how is evolving, is evolving to be more aggressive, less aggressive. This kind of things we would like to, we have genomic data, so we would like to be able to understand this part, because also this is part of the problem, with the evolution of the virus in different settings, in different environments.
This is interesting because the message here in France is that the virus has mutated, but there has not been that many changes. You're saying it has mutated significantly?
We are looking into it. We don't know. We are looking into it. Even within the city of Rio, we don't know how, different municipality, what is circulating. Because I say Ecuador is very small. If in Ecuador, they were circulating 4 different strands,
crazy, huh? Wow.
In Ecuador, it's not as much visited as Rio, and this was some months ago. So the curiosity is now what is circulating here,
Right.
So this is the interesting things that is the same thing circulating everywhere, or where there are tourists are circulating some other stuff, or I don't know. This is part of the problem as well.
Sure.
Because it's more or less aggressive. We don't know, and so this world task force in the labs, they're kind of analyzing the past months, 6 months of data, and so this is why need some help from people doing statistical genomics, because we have all this huge database, genomic database.
Okay.
Yeah.
And in Brazil, they have observed the same the same strands or different.
I know that someone commented that there was some paper. I think it was not in Rio, in some other city, about the strands of things, but I don't know if it was, as I said, just in that moment. But we haven't seen anything so far that at least I've seen about the evolution,
Mm-hmm.
Okay, you have it here, and how does it evolve locally, so this is one thing that we'd like to see, how things has been evolved, and how this, again, how this evolution can be related to the lockdown and no lockdown, like this mixing is not only people mixing, it's virus is various if this people mixing might increase mutation also, you know, this kind of so this is one aspect that I think has to be considered. But yes, so this is why it will be good to talk about your genomic your genomic colleague about this aspect at least, and maybe it can be linked to some other feature of your model, you know, some evolution of that parameters, you know, like as you mentioned, you know, you were already considering that the parameter have two different values, but this enters your infectious parameters, I think, in a different way. And somehow I think it's due to mobility as well, especially we see this with dengue. We see this with dengue where, you know, different towns, they're apparently they look similar, they have very different behavior.
Interesting.
Yeah.
Maybe some of your students or maybe people in the audience have some questions.
Yeah, let's see. We have people.
Hi everyone. May I do a question?
Yes.
Oh, okay. Hi, Jan.
Hello.
Hello. Congratulations for your talk. It
Thank
was
you.
very inspiring and very interesting model, by the way. But
can you introduce where you're from? Which because it's good to.
Yeah, I don't see you.
So
sure.
So actually, which department?
Sure. Sorry for that. I'm from UFRJ and do systems engineering and computing there. I'm a doctoral student and I'm advised by Daniel Figueiredo. Okay. And it's a simple question about your model. I've seen that you modeled the deconfinement as an increasing on the force of infection, right? The force of infection alpha.
Right.
Okay. My question is, would it make sense? Would it be feasible? And what would be the implications to model this deconfinement as a kind of birth dynamics, in the sense that some susceptible individuals were previously untouchable, so to speak. But suddenly, because of the deconfinement process, they are now taking part in the system and are then subject to be infected. So instead of increasing the force of infection, I would be introducing as a kind of birth dynamics, I would be introducing no susceptible individuals in the system. Does it make sense? Would it be any different from the results you already have? This is my question.
Yeah, it's a very good question. Mathematically, it seems that's what I asked the same question to my Mexican colleague who's more of an expert on the SI than I am, at least for the epidemic point of view. Let me go back to the model in the first. Am I sharing? Yeah, I'm still sharing. So let me show you the model. For me, it makes sense what you're saying. You're suddenly increasing the capacity. If you're increasing you're increasing the number of susceptibles, how do you increase the number of susceptibles?
I think what he means is that is a sort of birth.
Right.
It's like having birth of new susceptible. It's just because they can get there instead of before. that before is a source of susceptible that
Maybe, yes, yeah, in that way, yes. But again, from the discussions with my collaborators, really what's happening is you're changing the alpha. You see, for example, let's take the situation, a practical situation. You isolate what happened in Sweden, for example. In Sweden, they let they didn't isolate the country. They isolated only people who were at risk. And when they relaxed the lockdown, I mean the isolation, what happened was that some of the people who had it infected the people who did not have it. So in real, I mean to understand it, it's really your contact that's increasing. The size of the reservoir, it's essentially the population of the city. You don't change this. You see, you bring in new you bring in new susceptibles because you're increasing the contact. But you can't really bring new susceptibles as such, keeping alpha constant. You're increasing alpha S by increasing alpha. You see what I'm saying?
Yes, I understand.
Yeah, that's the way it should be understood.
Okay, you entirely answered my question.
Okay.
Okay. Just one another question from slide 33.
Okay.
Yes, there you presented some plots. Yes, this one. These refer to daily cases per capita. And I was wondering why per capita would a diagram from daily cases only would the curves, the shape of the curves would be any different from these instead of a per capita version?
I think it's to compare. Exactly. You have to normalize, otherwise you don't know.
Okay.
You don't have a feeling.
Yeah.
Okay.
That's exactly.
Nice.
Yeah, because you have small countries, for example, Jordan. You see, it's a small country. It's almost. I think Jordan is like 12 or 13 million.
That's for comparison reasons.
The United States, right. 300 million. So you really want to compare.
Nice. Okay.
It happens the same here in Brazil. If you look at the number, it looks everything is happening in Rio, but then when you normalize, you see that actually it's much worse somewhere else.
Right.
It had to kind of normalize with respect to some significant population, the appropriate population. Otherwise, you don't see things.
Right. How is the situation in the Nordeste?
I have to tell you the truth. I'm going to look now because of COVID, we have Cesar Castillo that is looking there. He's the chief, but I'm going to look now because we're also keeping interested in dengue and other stuff. So we decided to compare with Recife and some other town in the Nordeste. But usually for dengue, they're out of phase with Rio, for example. So, okay. But I will be interested to see with COVID. I haven't looked, honestly. I haven't looked.
Okay. Is there any interaction between dengue and COVID?
I don't know, but what happened that it seems a strange, I mean, we have tuberculosis is endemic here in Rio, for example. I learned this, I didn't know. Honestly, my ignorance, I thought that tuberculosis, we had vaccine and so on, by ignorance, because only kids are vaccine for tuberculosis. So adults, there is no vaccine. And then what we see that somehow some in the community, in the favela, people got first COVID, and then the same people might get tuberculosis. Okay. We have the two. I don't know if it's just I don't know how tuberculosis is bursting after COVID, if it's a pure coincidence or it's not. But we had in Amazonia already before in March, they had coexistence of tuberculosis and COVID and H1N1. Wow. So who knows how, if again, it's a coincidence or really one get the other. And in all this, the dengue part has been, no one talks about dengue or chikungunya and so on so much. So we have to go back and look at this data. But for sure, tuberculosis it's something very present.
Okay. Wow. Okay. Wow. This is, yeah. Okay.
Well, actually, I have to tell you that Ronald, that I remember, is doing some very interesting work on network dynamics.
Who is?
Ronald.
Okay.
With his advisor, Daniel. Yeah, hey, Daniel mentioned a lot of his work now.
Okay. Okay. Hi, Ronald.
Yeah,
you,
but
Ronald, were you the one?
That's why I was particularly interested.
Okay, I'm glad.
But I think they do some stochasticity, no? You have also some stochasticity, no? You add
definitely. We work with markup chains, but we also try to explain a full model by a mean field approach, just like is being doing here. But we are actually working with an SIS model, but there are many similarities and many intersections.
Yeah, they kind of say that if the person knows that there is a possibility to get infected, people stay away from the infected. They use rationality of the. I think in Rio, this is not so much. This is very cultural. People, they think of being together is so much stronger that about being aware that there you might get. So it's very cultural related, I think. But they do this interesting thing that if people were rational, then they would avoid. And also some conscience. You're infected, and then you kind of. You avoid to spread around, so but it's interesting.
Yeah, Ronald, did you write something up on this?
Oh yes, I did. I can provide you a link.
Send it to me?
Yeah, sure. Just give me 1 minute for me to take the link and put it here in the chat. But we investigate protection effects. We assume that agents will somehow try to protect themselves and then try to understand the implications on a networked model given mobile agents. So the dynamics are very different. But I'll bring this to here, but give me a couple minutes.
Sure. It's very interesting. So these are agent models.
Oh yes, it's a mobile agent model, in practice, when we talk about mobile agents, generally we are talking about a square-shaped region and a continuous mobility through that region, and through proximity, one decides if an agent gets infected or not. But we do a different thing. We assume that agents move through the network nodes. So the node is not an individual, but it's a site, and the agents move across these sites through the edges.
Interesting. Okay, and you can do a mean field approach of this thing?
Yes, we can do these actually. I'm trying to find here my point. Oh, okay, I just got it. Oh,
Okay.
I'll put it here in the chat, and that's the thing. We have two models operating. One is the full model, the mobility model, which introduces protection and so on and so forth. And we have the ODE model, the mean field model, that tries to explain what we are simulating.
Okay.
So,
interesting.
and here it is in the chat.
Let me take a look.
Okay.
Okay. That's interesting. Yeah. Let's see the equations. So you take an undirected network.
Yes.
Mm-hmm. Okay. So you're assuming something like an SI as well?
Yes, SIS.
SIS, okay. D'accord. Why SIS?
Well, it's mainly because there are few works. Actually, this is the first work on this approach, and SIS allows for rich dynamics. We were interested on the mathematical capabilities we could work upon, and this is basically the main reason. We could work with other compartment, but SAS is one of the main models adopted, and it would be good to see that in practice.
Okay, I'll look at it. I'll read it and see if I'll get back to you.
I'm really happy with that, with this opportunity. I should say I'm honored with your attention on that matter. But I'm anticipating I'm looking forward for your return on that. Thank you very much for your feedback.
Thank you.
Thank you very much.
Yeah, thank you, Ronan.
Okay, so I think thank you for the very inspiring talk.
Thank you, Stefanella.
So if anything else, we can close.